So what if I told you that a single mistyped keystroke by a network administrator could take an entire global enterprise offline in a split second?
Oh, yeah. I mean, it happens way more often than you'd think, honestly.
Right. Like we just expect instant magic when we stream a video or whatever.
Yeah.
But behind the glass of your screen, there's this incredibly complex, totally invisible set of rules.
Yeah, a massive set of rules.
Exactly. Rules governing exactly how that traffic flows and keeping the whole system from just totally collapsing.
It really is this high-stakes choreography, you know? Like, we usually only notice the infrastructure when it physically breaks.
Yeah, when the Wi-Fi is down.
Right, exactly. But there's this immense amount of logic running under the surface to ensure that, like you said, a single bad keystroke doesn't actually bring down the whole internet.
And that is exactly what we are getting into today.
Yeah.
So whether you are actively prepping for the JN0-106 exam or you're just a learner who wants to understand those invisible rules of the road, you are definitely in the right place. Our mission for this deep dive is to deliver basically a masterclass on the key technical concepts of the JN0-106 exam. We aren't just handing over an answer key here.
No, that wouldn't help anyone.
Right. We are mapping out the actual problem-solving logic for 10 real practice questions.
Which is, honestly, the absolute best way to learn it. Understanding how to solve these specific questions translates directly to understanding how modern networks actually function out in the real world.
So just for some foundational context, the JN0-106 associate-level written exam is basically a 90-minute gauntlet.
A very fast 90 minutes.
Yeah, seriously. You're facing 65 multiple-choice questions delivered in English. So to simulate that vibe, I'm going to read the full text of every practice question and all 4 options aloud, exactly as they're written.
Sounds like a plan.
Then we are going to tear them apart. Let's start right at the macro level. How do networks handle the sheer volume of modern traffic?
The big picture.
Right. So here is the first question on the docket. In the context of network traffic management, what is the primary objective of implementing class of service mechanisms?
Okay, let's hear the choices.
Option A, to automatically detect and block malicious traffic patterns entering the enterprise network. Or B, to dynamically increase the physical bandwidth capacity of highly congested network links.
And the other two.
Option C, to prioritize specific types of network traffic during periods of congestion to ensure acceptable performance. And finally D, to encrypt sensitive data payloads before they are transmitted across untrusted network segments.
Okay, so where is your head at with this one?
Well, I was initially leaning toward B, actually. Like, if a network is highly congested, wouldn't the primary goal be to dynamically increase the physical bandwidth capacity? I mean, we want a wider highway, right?
It's a completely logical thought, yeah.
Yeah.
But it actually highlights a hard physical limit of networking. You can't magically build a new physical copper cable.
Or a fiber optic link.
Exactly. You can't build that using a software mechanism. Class of service, or COS, is entirely about managing limited resources, which makes C the correct answer.
To prioritize specific types of network traffic during periods of congestion to ensure acceptable performance.
That's the one.
So it's more like a VIP fast pass lane at a crowded theme park, right? Doesn't build new roller coasters. It just decides who gets to ride first when the lines get long.
That is exactly it. And to take that VIP lane analogy even further, if the park is completely empty, everyone just walks right onto the ride.
No line, no waiting.
Right. COS only really kicks in when the park is at full capacity. Like when bandwidth is constrained, a live voice or video call needs to happen in real time.
Oh yeah, nobody likes a laggy Zoom call.
Exactly. Whereas a bulk file download, that can wait an extra few milliseconds in the queue without anyone noticing.
That makes total sense. And I'm assuming A and D, so that's blocking malicious traffic and encrypting data. Those are just entirely separate security functions.
Spot on. They are super vital, obviously, but they have absolutely nothing to do with queuing and prioritizing packets.
Okay, cool. But to prioritize that traffic, you first need to be able to identify and address the billions of devices sending it, which brings us to the structural evolution of the Internet Protocol.
Ah, yes. The big shift.
Right. So question 2. From a foundational networking perspective, what is the primary structural difference that distinguishes the next-generation Internet Protocol from its predecessor?
Let's run through the options.
A. The next-generation protocol entirely eliminates the concept of network routing in favor of direct peer-to-peer connections.
Okay.
B. The next generation protocol relies exclusively on physical media access control addresses for global internet routing. C. The next generation protocol operates solely at the transport layer to ensure guaranteed end-to-end delivery. Or D. The next generation protocol utilizes a significantly expanded addressing architecture to accommodate a massively larger number of unique devices.
All right, what's your take?
Well, when I hear next generation in tech, it almost always implies a massive leap in speed, like gigabit fiber or something. But none of these options even mention making data move faster.
Yeah, that's a classic trap. That's because the impending crisis wasn't about speed, it was about real estate.
Real estate.
Yeah, the correct answer is D. The next generation protocol utilizes a significantly expanded addressing architecture. We are talking about the jump from IPv4 to IPv6 here.
Oh, great.
The IPv4 uses 32-bit addresses, which gave us about 4 billion unique IPs. And, that sounded infinite back in the 1980s.
But not so much anymore.
Not at all. Today, when your refrigerator, your thermostat, and, your watch all need an IP address, we literally ran out of room. So IPv6 uses 128-bit addresses, which provides an almost unfathomable amount of unique identifiers.
Just to play devil's advocate for a second, what about A, eliminating network routing for direct peer-to-peer connections? That sounds like a pretty radical next-generation idea.
I mean, it sounds very futuristic, but it would completely break the internet.
Wait, really?
Oh, yeah. Routing is the fundamental concept of how data navigates the globe. You can't just eliminate it. Option B is also a trap because MSC addresses are used for local network communication on a switch.
Not for global internet routing.
Right. And option C just mixes up the OSI model. IP operates at the network layer. The transport layer is where protocols like TCP step in to handle the guaranteed delivery part.
Got it. Okay, so we have this massive 128-bit addressing system. But mathematically, a router crunching those huge numbers could easily crash under the weight of processing it all during a major internet event.
Oh, absolutely. It's a heavy lift.
So how the hardware physically prevents this is fascinating. Let's look at the next scenario, question 3. During a period of severe network congestion, how does the physical separation of the control and forwarding planes benefit the overall system operation?
All right, let's hear the choices.
Option A. The system automatically duplicates the forwarding table across multiple external servers for immediate load balancing. Option B. The system can compress transit data payloads in the control plane before sending them to the forwarding plane.
Got it.
Option C. The control plane can temporarily assume forwarding duties to alleviate pressure on the primary data path. And D. The forwarding plane continues to process network traffic without interruption, even if the control plane is heavily burdened with processing routing updates.
So, any initial thoughts?
I really want to pause on option C. Logically, if a construction crew is overwhelmed with work, the architect or the manager can step in, grab a hammer, and just help temporarily assume those duties to alleviate pressure, right? Why doesn't a router work that way?
That is a really great observation, but it gets to the heart of how specialized router hardware actually is. The control plane's CPU is like a math genius.
Okay.
It handles complex routing tables, it talks to other routers, but the forwarding plane, or the data plane, uses highly specialized ASIC chips designed to do nothing but push millions of packets per second.
Oh, so they're totally different types of processors.
Exactly. If you suddenly pushed 1 million transit packets up to the control plane's CPU to, help out, it would instantly spike to 100% utilization.
And crash the entire box.
And crash the whole box, yeah. So keeping them strictly isolated is the only way it works, which is why D is the correct answer.
The forwarding plane continues to process network traffic without interruption.
Right. The control plane does all the heavy math and basically hands a simplified map down to the forwarding plane. If a massive network outage causes the control plane to frantically recalculate all the maps, your active YouTube stream
flowing through the forwarding plane
wasn't interrupted at all. Yeah. They operate totally independently.
Which also completely rules out B, I guess, since the control plane doesn't touch transit data payloads at all.
Exactly. And A is just describing external server load balancing, which has literally nothing to do with the internal architecture of a single router.
Right. Okay, so that separation of powers keeps the hardware humming. But what keeps the human administrator from, accidentally taking the system down with a bad keystroke?
The dreaded human error.
Exactly. Let's talk about safety nets. Question 4. Describe the fundamental advantage of the candidate configuration mechanism in the Junos operating system.
Okay, lay 'em out.
Option A. It automatically reverts the system to factory defaults if an error is detected during boot. Option B. It prevents configuration changes from immediately impacting the active state of the device until explicitly validated and applied. Option C. It provides a real-time backup of the configuration to a remote server without administrator intervention. And option D. It completely eliminates the possibility of human error when deploying complex routing policies.
Wow.
I have to admit, option D really caught my eye. Completely eliminates the possibility of human error. I mean, that sounds like the ultimate software feature.
Man, I wish. But it's physically impossible.
Really?
Yeah. You can write a technically perfect configuration that routes all your corporate traffic into a black hole. The syntax is flawless, so the router will happily accept it.
But it's operationally disastrous.
Exactly. No software can fix bad human logic.
So it's more like a drafts folder in an email client. You can write your message, review it, and make sure you aren't replying all to the whole company before you actually hit send.
That's the exact mechanism, yeah. The correct answer is B. In a lot of older networking systems, the moment you typed a command and hit enter, it went live instantly.
Oh, wow.
Yeah, if you mistyped an IP address, boom, you instantly disconnected a whole office. But Junos uses a candidate configuration, which is basically a sandbox. You build it, you review it, and then explicitly issue a command to make it active.
And just to close the loop on this one, it definitely doesn't automatically revert to factory defaults on a boot error, like option A suggests, right?
Oh, that would be an absolute nightmare. Imagine a temporary power blip causing your core router to wake up and wipe its entire brain back to factory settings.
Yeah, you'd be fired.
Fired instantly, yeah.
Good to know. But what happens if you do hit commit on a terrible configuration and you manage to lock yourself entirely out of the device?
The panic moment.
Oh, right. Question 5. What is the specific purpose of establishing a rescue configuration on a device running the Junos operating system?
Let's see the options.
A. To provide a known working configuration state that can be quickly restored if a recent configuration change isolates the device.
Okay.
B. To provide a permanent backup of the system software image in case of flash memory corruption. C. To automatically bypass the authentication process if the authentication server becomes unreachable.
And D.
D. To automatically fail over hardware processing to a secondary routing engine during a hardware fault.
So what are you thinking here?
I'm leaning toward A. It sounds like an emergency ripcord. But how is A different from B, backing up the system software image? Like, aren't those doing the same thing?
Not quite, no. So the system software image is the entire Junos operating system. We're talking gigabytes of base code.
Yeah.
But a configuration file is just a tiny text document containing your specific IP addresses and rules. A rescue configuration, which makes A, the correct answer, by the way, is a known working baseline of that text file that you specifically saved earlier.
Got it. So if I commit a change that severs my connection?
Right. Someone can just plug a laptop directly into the router physically and just roll back to that rescue file without reinstalling the whole operating system.
That's incredibly handy. What about option C, though? Automatically bypassing authentication if the server is down.
Yeah.
I mean, if I'm locked out because of a bad config, bypassing the password seems pretty helpful.
Helpful for you, sure, and immensely helpful for every malicious hacker scanning your network.
Oh, right.
Yeah, never bypass authentication. It's a catastrophic security risk, and Junos will never, ever do that by design. And option D is also off base because it's talking about a physical hardware fault, not a configuration issue.
Speaking of security, that brings up a really critical point. You can't even begin to set up these configurations until you lock the front door of a brand new piece of hardware.
Gotta secure it first.
Always. Let's look at initial setup. Question 6. Before a newly unboxed Juniper device can fully participate in network routing using its factory default state, what mandatory administrative action must be completed?
Options.
A. The administrator must explicitly disable all default security protocols. B. The administrator must connect a dedicated management terminal to a specific physical port. C. The administrator must configure a system root authentication credential. Or D. The administrator must establish an active internet connection to validate the hardware license.
Any red flags jump out at you?
Well, I'm looking at option A, which literally says disable all default security protocols. Why would anyone ever intentionally weaken the initial state of a device?
It's actually a brilliant distractor for people used to older, less secure consumer platforms.
Really?
Yeah, like where you sometimes had to turn off the firewall just to get basic connectivity working out of the box. But in enterprise routing, that is sacrilege.
It's definitely not A.
Definitely not. The correct answer is C. Junos operates on a strict secure by default posture. The system absolutely refuses to let you commit any routing configurations on a brand new device until you have set up a root password.
Okay, that makes sense. And I'm guessing routers don't need to phone home to the internet to validate a license just to start pushing packets, like option D suggests.
Exactly right. They are autonomous devices. And option B is false because while you can use a dedicated management port, it isn't mandatory. You could just as easily configure it over a basic serial console cable.
All right, so our device is locked down and safely configured. Now we have to look at the exact logic it uses to make decisions when faced with multiple different paths to the exact same destination.
Route selection. This is a big one.
Yeah. Question 7. When evaluating multiple paths to the same destination learned through different protocols, which underlying mechanism does the Junos operating system use to select the active route?
Let's hear the 4 choices.
A. The system selects the route associated with the strictly lower protocol preference value. B. The system selects the route with the highest available bandwidth across the entire path.
Okay, 2 more.
C. The system always prefers the dynamically learned route over a manually configured static route. And D. The system uses a random selection algorithm to load balance across all available protocols.
Yeah. What's your intuition here?
Well, like, if I'm driving, I want to take the widest highway. Logically, the system should just select the route with the highest available bandwidth, like option B suggests. Why wouldn't the router just pick the fastest link?
It comes down to comparing apples and oranges, basically. When evaluating paths from entirely different routing protocols, say an OSPF dynamic route versus a static route, a human-typed in bandwidth actually isn't the deciding factor. Trust is.
Trust.
Yeah, and that makes A the correct answer. Junos assigns a default preference value to different protocols. A strictly lower number means it is more highly trusted. The router essentially asks, which map maker do I trust the most?
So it's about the source of the information. Like if I plug a cable directly between 2 routers, a direct route, does that have the lowest preference?
Exactly. Direct routes are implicitly trusted because they are physically connected, so they have a very low preference value.
Okay, I follow.
A static route configured by an admin is slightly less trusted, and a dynamic protocol like OSPF is even less trusted than that, which actually knocks out option C. Junos trusts static routes more than dynamic routes by default.
Oh, interesting. And obviously D, random selection, would just be total chaos.
A complete chaos.
Routing requires absolute deterministic logic, not a dice roll. But what if a single trusted map has overlapping destinations?
That happens all the time.
Let's see how it handles that.
Question 8.
When a router evaluates a packet against its active forwarding table containing multiple overlapping destination networks, what criteria dictates the final path selection?
Options.
A. The router selects the path associated with the most specific mashing network prefix. B. The router selects the path that was most recently added to the forwarding table. Right.
C. The router dynamically balances the traffic equally across all available matching network paths. Or D. The router selects the path with the lowest numerical interface identifier.
What do you think?
This feels like a mail carrier comparing a zip code to an exact street address. Like, if I have a letter for a specific house, I don't just drop it off at the town border because the zip code technically matches. I deliver it to the most specific address available.
And that is exactly how the router thinks. You nailed it. The correct answer is A. This is called the longest prefix match rule.
Longest prefix match.
Right. Under the hood, the router is literally comparing the binary bits of the destination IP address against its routing table. If it has a broad path where 16 bits match, known as a /16 subnet, and another path where 24 bits match, a /24 subnet,
It goes with the /24.
it will always route the packet down the more precise /24 path.
Okay, but I was actually looking at option C, dynamically balancing the traffic equally. If both the /16 and the /24 technically match, why not just split the load and send half the traffic down each path? Because they aren't equal matches, one is a massive generic bucket and one is a precise location. Using your mail analogy, sending half your letters to the city border and half to the actual house is terrible delivery.
Right. Yeah, that makes sense.
You always go with precision. Option B, chronological order, is totally irrelevant. And D, the numerical interface identifier, has absolutely no bearing on logical IP destination matching.
Cool. So to understand where these complex maps come from in the first place, let's zoom in on one of the most common dynamic protocols out there.
Let's do it.
Question 9. Which statement accurately describes the default routing policy behavior for the open shortest path first protocol within the Junos operating system?
OSPF. Let's hear the options.
A. It automatically redistributes all active static routes into the routing domain without user intervention. B. It requires an explicit configuration policy to accept any incoming topology updates from adjacent peers.
And the others?
C. It advertises all active direct routes, but rejects updates from other routing protocols. D. It naturally floods topology information to peers, but strictly does not export routes from other protocols into its domain by default.
So what's your take on OSPF?
I'm really curious about A. Automatically redistributing all active static routes into the domain sounds highly efficient. Like, why wouldn't it just do that?
Efficiency without strict boundaries is exactly how you get catastrophic routing loops.
Oh, yikes.
Yeah, the correct behavior is D. Open shortest path first, or OSPF, is incredibly chatty inside its own borders. It eagerly floods topology data to all its OSPF neighbors to build a complete map, but it is deeply conservative about outside information.
So it won't just share everything.
Right. If you have a private static route to an internal HR server, OSPF will not automatically blast that out to the rest of the network.
So you have to explicitly build a policy to tell it to share that specific information.
Exactly. Defaulting to strict boundaries protects the integrity of the network. That also explains why B is wrong. OSPF inherently accepts updates from peers. You don't need a policy to accept them, only to export them.
Gotcha.
And C is incorrect because OSPF doesn't automatically advertise all active direct routes either.
All right, well, protecting boundaries is actually a perfect segue to our final topic. We've established how traffic is prioritized, addressed, secured, and routed. Now we need to look at what the router does with traffic it explicitly wants to block.
Oh, firewall filters.
Yes. Question 10, the last one. When designing a firewall filter, what is the operational difference between the reject action and the discard action?
Okay, let's hear the final choices.
A. The reject action silently drops the packet, while the discard action logs the event to the system messages. B. The reject action drops the packet and sends an unreachable notification back to the source, whereas the discard action drops the packet silently. C. The reject action forces the packet to take an alternative routing path, while the discard action removes it from the network completely. And D. The reject action applies only to transmission control protocol traffic, while the discard action applies only to user datagram protocol traffic.
So reject versus discard.
I love the analogy for this. A reject action is kind of like a polite bouncer checking your ID and saying, sorry, you aren't on the list, you have to go home.
Right.
But a discard action is like a bouncer who just stares at you silently through the glass while you wait outside on the sidewalk forever.
That is brilliant. And in cybersecurity, that silent bouncer is highly effective. B is the correct answer. The critical difference is the feedback loop.
The feedback loop.
Yeah. When you configure a reject action, the router drops the packet and generates an ICMP unreachable message back to the sender. It explicitly says, connection failed. But when you use discard, it just deletes the packet from memory.
So the sender gets absolutely zero notification.
None. Their machine just hangs there waiting until the connection times out.
Wait, look at option C, though. It says the reject action forces the packet to take an alternative routing path. Like if a bouncer turns me away, I just go to a different club. Does the packet do that?
No, because a firewall filter is a rigid wall, not a traffic cop. Its job is solely to permit or deny. If you hit a reject rule, that packet is killed on the spot, not detoured.
Okay.
Option A reverses the reality of the two actions, and option D is just arbitrary. You can apply reject or discard to both TCP and UDP traffic equally.
Best of luck to you as you continue your learning and conquer the JN0-106 exam. Until next time.